And now I'd like to introduce our special guest for today. We're very delighted to have with us Dr. Fulvio Melia. He is the chairman of the physics department at the University of Arizona at Tucson, one of the centers of black hole physics. And he's the author of a new book called The Edge of Infinity, about black holes. So let's now get a few definitions off the ground before we head right into the center of a black hole. First of all, what is a black hole? Well, a black hole is an object whose escape velocity is the speed of light. In other words, light itself cannot escape a black hole. In other words, everything falls in, but nothing falls out. And then surrounding the black hole, there is a sphere called the event horizon. And the event horizon is the point of no return. If you fall through that imaginary sphere, you get sucked right into the black hole, and you never come out again. And lastly, we have two types of black holes. Stellar black holes, that is, old stars that peter out and collapse into a black hole, and galactic black holes, like at the center of the Milky Way galaxy itself, right in our own backyard. So once again, our special guest today is Dr. Fulvio Melia, and we are talking about one of the strangest objects in the universe, and that is the black hole. The first question for you is, how did you first get interested in physics and astronomy?
Well, I actually grew up in Melbourne, and I don't know if all of your listeners have had the opportunity of visiting the Southern Hemisphere, but looking up at the sky from the Southern Hemisphere, one gets quite a different view than from the Northern Hemisphere. The Milky Way, for example, is very easily seen, and it stretches from one horizon to the next, and it fills the cosmic vault. And when I was small, I remember almost every evening just going outdoors and just looking at the stars in the Milky Way for hours and hours and hours. And I would say that that's probably what started me off. With that, of course, comes the natural curiosity of how things work and what these objects are, and one is led, I think, in most cases, to a study of physics, and that's what got me into physics and astronomy, I would say.
And Arizona is one of the world's leading centers for astronomical research, I understand. So what is it like to be in Arizona versus being in New York City, to be able to look up at the night sky and see the Milky Way, and also to be at the very forefront of telescope technology?
Well, that's the interesting comparison, of course, because even though I usually tell my friends, especially the ones overseas, even though we belong to the same country, the southwest of the United States is really very, very different from the northeast, as I think everybody realizes. Here in Arizona, the skies are almost always clear. It's not a coincidence that many of the national and now the international telescope facilities are being built here. We get very little cloud cover during the year, so going out in the evenings, whether using a telescope or not, presents quite a glorious experience. It's a wonderful opportunity to feel the magnitude of the skies and the objects there. And of course, for research, especially for the observers and people who build instruments eventually placed on the telescopes with which these observations are made, there are very few places on the planet better than this to do studies such as this. The clarity of the skies and also the access to objects not only in the Northern Hemisphere, but those approaching what one would see from the Southern Hemisphere. Of course, Earth's rim prevents us from seeing all of the portion of the Milky Way that would be accessible from the south, but nonetheless, during a portion of the year, we could still see the center of the galaxy, for example, which is close to the southern horizon for us here in Arizona. But other than the skies here, the only other place that would present a comparable opportunity for studying these objects would be from countries such as Chile, which, of course, is way down south. So as far as we here in the United States are concerned, unless we want to travel to South America, this is probably the place to do this type of work.
And also, tell us a little bit about how stars die and the formation of black holes.
Right. Well, this, of course, is an ongoing investigation. We think we understand some pieces of the puzzle. Not everything is known. It's quite a long story. Black holes can actually form in several ways, and it's not clear that the supermassive objects that we see in the nuclei of galaxies form through the stellar process of life and then death. They may have formed in other ways, and we may come back to this in a few moments when we talk about the genesis of these objects early on after the Big Bang. But in terms of the smaller black holes, like the ones like Cygnus X1, for example, the objects that we think weigh perhaps 10 to 20 times as much as the Sun, as far as these objects are concerned, most of them are produced when a very massive star, and by very massive would mean an object that weighs anywhere between 30 to 50 times the mass of the Sun, burns its nuclear fuel rather quickly, it turns out, because the more massive the object is, the faster it burns the fuel, and then eventually loses that internal support that prevents it from collapsing to the middle. It's the heat generated from nuclear burning that preserves the star during the main part of its life, like the Sun is now. And at the end, when that nuclear fuel is burned to heavier elements such as carbon and eventually to iron, the heat generation stops and the material can't support itself anymore and collapses into the middle, at which point a supernova explosion ensues, and the remnant, depending on how massive the original star was, can sometimes be a black hole with a mass somewhere between a couple of solar masses and 10 to 20, as I said earlier. So the vast majority of black holes about which we know, and there are some billion of these in the galaxy, probably formed in this way. But there is another class of objects, like the one at the center of our galaxy and the center of many other galaxies, such as the Andromeda galaxy, our sister galaxy. These objects have a mass anywhere between 1 million to several billion times the mass of the Sun. And although some of them may have started as seeds from supernova explosions a long, long time ago and eventually have grown to the point where they are now, it's not clear that all of them could have formed that way. And the reason I say that, and this would lead into another part of the story, the reason I say that is that we now have very, very strong evidence that at least some of these supermassive objects were formed only 700 million years after the Big Bang, much, much earlier than the formation of galaxies and much of the structure that we see in the universe today. So it's starting to look like there was some other mechanism, some other process that led to this early collapse and this catastrophic creation of very strong gravity surrounding these objects, which probably also then acted as nucleation sites that attracted other matter towards them. And that matter, we think, in many cases, may have led to the formation of galaxies. So the odd thing now is that we may actually owe our existence to the formation of these supermassive black holes, because they may have been the seeds that created galaxies, which then, of course, created stars within them and planets and life and so on. So it's quite a long, complex story, and we don't know all the details yet, but some of the pieces of the puzzle are starting to emerge, in that there definitely appear to be several classes of these, and one class having to do with the supermassive objects somehow had a genesis much, much earlier than we thought before, and how they formed is not entirely clear yet.
Well, I have a question that many young people ask about black holes. First of all, black holes suck in everything. Even light itself cannot escape. In some sense, they're the ultimate roach hotel, and the Hubble Space Telescope has photographed black holes eating up whole star systems. So in other words, things check into a black hole, but nothing ever checks out. Well, then the question is, well, a black hole should be invisible. Even light itself cannot escape from a black hole. Therefore, a black hole should be invisible. And yet we have the Hubble Space Telescope taking photographs of perhaps hundreds of black holes in outer space. And so then the question is, how do you photograph something that is invisible?
Right. This is what's really generating much of the excitement these days with theoretical astrophysicists and, of course, the physics community in general. what telescopes that have been built up to this point have seen so far is not really the black hole itself, but what they see is light produced by matter falling into the black hole. Their resolution is not yet good enough for them to make an image of the black hole itself, the event horizon, which is the surface beyond which nothing can escape, including light. So if we really could see the black hole itself, what we would see is a dark shadow in front of a curtain of light. The curtain of light presumably would be produced by matter behind the black hole relative to us, and the black hole would absorb all of the light produced behind it or redirect it away from our line of sight, because gravity can bend the path of light, and so we would see a dark shadow. That's what a black hole would look like if we had a camera with such clarity, such spatial resolution that we could see detail down to that size. It does look like by the end of the decade we may have the capability of actually forming such an image. But for now, telescopes such as Hubble and Chandra have not been able to do that yet. So instead what they show us is images, or what they produce is images of matter falling into the black hole from larger distances much further away than the event horizon itself. Both have done spectacularly in this regard, though. Both Chandra, the X-ray telescope, and Hubble have each produced a very deep image of certain patches of the sky. By deep, we mean that there were patches in the sky, such as one in the constellation of Ursa Major, where there are very, very few objects within our own galaxy inside of that patch, and so it's like looking through a relatively open window to much distances much further away than objects within our galaxy. And what they were able to do by staring at these patches was to collect light from objects some 10 to 12 billion light years away. In other words, objects that were producing this light only 7 to 8, 900 million years after the Big Bang. And what they see when they look at these patches is very bright objects, either X-ray objects or ultraviolet or infrared objects in the case of Hubble, objects that number as many as 500 within a region only the size of the full moon. So if you can imagine with your eye looking at a part of the sky that has the size of the full moon, within such a region, these telescopes have been able to produce images of as many as 500 of these objects. And these objects are so far away, they're so bright, that the only way that they could produce this much light is if they're black holes absorbing matter from their environment and converting gravitational and rest mass energy into light. So we believe that when we look at these patches, most of the objects that we see, most of the 500, must be supermassive black holes at that distance in the universe. And what's interesting is that when one extrapolates over the whole sky, these numbers correspond to total numbers of some 300 to 400 million such objects. And we know that that's not all that's there, because that's what we can count. That's what we can see. But some of these objects are probably also obscured by dusty matter falling in towards them, and so it's not clear that we're seeing everything. So the best that we can say is that there must be at least 300 million of these supermassive black holes spread throughout the cosmos. Chandra, of course, has gone on and done even much better than that. It's allowed us to look at the supermassive black hole at the center of our own galaxy with even better clarity because it's much closer than the others. It's only 25,000 light years away compared to the 12 billion light years of many of these other objects near the beginning of the universe's life. And because this object at the center of our galaxy is so close, we've been able to study it with Chandra and now other instruments as well. The European Space Agency has its own X-ray telescope called XMM Newton, which has done similarly spectacular studies of these objects. But with Chandra, we've been able to see the X-rays produced by the black hole at the center of our galaxy with enough resolution that we can actually place the source, the location of the emitting plasma, within a region no bigger than the distance between the Earth and the Sun. In addition, this object seems to explode roughly once a day, producing a flare of X-rays. The X-ray intensity during these events goes up by anywhere between 30 and 200 times what the intensity is during the quiescent state. And so for a couple of hours, the black hole at the center of our galaxy shines much, much brighter than it otherwise